So we've come back to finish off section 5.8. We're going to study logistic models, which use the following function right here. The population P of t at time t is given by c over 1 plus a times e to the minus bt. I have lots of constants going on here, a, b, and c. The number multiplying the exponential term is not p of 0. Okay, if you let t equals 0, you'll end up with c over 1 plus a. It's just not just a. It's a little bit more complicated. So they haven't actually told you a, b, and c represent specific things. Okay, they've just given you, hey, they're just constants. But this is logistic growth. Where this formula comes from is basically whatever you're studying wants to either grow or decay exponentially. But there's like a limiting factor, like it's a population of bacteria that's growing, but it's not going to go above a certain amount. And as it gets closer to that amount, the growth has to slow down. Those sort of assumptions lead to a differential equation that solves down to this. And if you take differential equations, so after this you could take Calc 1, and after that you could take Calc 2 and linear algebra, and then you can take differential equations, you'll study where this formula comes from. But for now, we're just going to use it. When b is positive, notice in this expression, b already has a negative sign in front of it, which means this is a negative exponent, but it's down in the denominator, which means really it's kind of like having a positive exponent. That's a growth model. Similarly, if b is negative, since it has a negative sign in front of it, that means that's positive, but since it's down in the denominator, it's kind of like having a negative exponent. That's a decay. And you can see what ends up happening is there are two horizontal asymptotes of 0 and c. So this is something that like wants to just grow, but as it gets closer to c, it's going to slow down. So this c is the horizontal asymptote. And here it's decaying. It started very close to c, but now decays down. So the main of this function, which I'll go ahead and write back up here, it was y equals c over 1, was it 1? Sorry. 1 plus a e to the minus bt. Okay, so the domain is all real numbers. Now, there's no problem plugging t into that exponential. The only thing you have to worry about is division by 0. But the exponential e to the minus bt is always positive. And remember that a was given to be a positive constant in the previous slide, so this is positive, and therefore this can never be 0. So the domain is all real numbers. The range, as we saw in the previous slide, it has two horizontal asymptotes at 0 and c, and it goes in between them. C is what's called the carrying capacity. It's the maximum possible value that the system can tolerate. If it's bacterial growth, for example, it can grow until a quantity of blank, of C, and that what inhibits growth past that point. There are no x-intercepts because you have that horizontal asymptote of 0 and you stay above it. It does have a y-intercept. It's just whatever you would get when you plug in 0. Okay, as mentioned, two horizontal asymptotes. We saw it's increasing when b is positive and decreasing when b is negative. And there is what's called an inflection point at half of the carrying capacity. So I'll flip back to the previous slide so we can see those pictures. And I'll clear off my inaccurate markings. So the inflection point is essentially where it changes from I'm growing, and my growth is accelerating. I'm growing faster and faster until I'm still growing, but I start slowing down. And this always happens at 1/2 of carrying capacity because you do have actually some nice symmetry here. So it's called an inflection point. This is a term you'll learn later on in calculus. But really it just means I changed from speeding up how I was increasing to slowing down how I was increasing. Okay. In the one on the left, it's increasing the whole time. It just goes from going faster and faster to a little bit slower. It is ranges from being concave up to concave down. Now, the term concave up and concave down, we only saw as it related to parabolas, concave up, concave down. There is a sort of more formal definition of what it means, but it's not going to be terribly important for us. But again, the graph is smooth and continuous. It doesn't have any jumps, etc. So let's do an actual example of working with it. So here is the logistic model for a particular yeast culture. What is the carrying capacity and the growth rate? That's just asking you to identify some terms from the formula. What was the initial population? What is the value when t equals? What's the value when t equals 5? What is the time when the population equals 250? And then finally, use a graphing utility to determine how long it takes to reach 1/2 of the carrying capacity. Okay, so pause here and do what you can. The formula is different from the cooling or financial or radioactive decay ones, but it's really still just about exponential stuff, so try to work it out. Okay, hopefully we did what we could. So, the carrying capacity is what happens as time goes to infinity. So as t goes to infinity, the population goes to 750 over 1. I'll just go back to that formula here. If time is going to infinity, this becomes a very large negative number, so this becomes very close to 0. So this becomes very close to 0, and you basically just have 750. Remember that number on top, if you're in your standard form of c over 1 plus a e to the negative bt, c is your carrying capacity 750. And what's your growth rate? Okay, the growth rate is just b, 52.6%. The initial amount is just what's p of 0, and if you plug p of 0 into that expression, e to the something times 0 is just e to the 0, which is just 1, and we just get 10. 74 plus 1 is 75, 750 75 is just 10. So we started off with 10 grams of yeast. How much do we have after 5 hours is just plug in 5. And you really have to use a calculator to get anything beyond this, but it's about 118 grams. So even though we started with 10 grams, we have gone all the way up to 118 grams. When will there be 250 grams? Well, now I'm setting the end result to be 250, but the time is unknown. Okay, so here's where we actually have to do a bit more work. Multiply the denominator across. Okay. Divide the 250, that simplifies things. Subtract that 1 over. Divide by 74. Take a natural log and divide by negative 0.526, because you'll end up with natural log of 1 over 37 over negative 0.526 is t, which gets me here. Now let me just ask you, this is a positive answer, but here I have the natural log of something and I'm dividing by a negative, so why isn't this negative? The answer is the log of 1/37 is already a negative number. Okay, I have a log with a base larger than 1, the curve looks like this. And the intercept, remember, was 1, 0. So if t is less than 1, the log of t is negative. I'm over here. If t is bigger than 1, the log of t is positive. So since I'm making the log of something less than 1, that numerator is already negative. So this is actually of the form negative over negative, which, yes, is positive. So it takes about 6.86 hours. So finally, when do I reach half the carrying capacity? In part A, we said the carrying capacity is 50, so half that is 375. So it's really the same as the previous problem where we are setting where is this equal to this. And here they said use a graphing utility, so okay, just have calculator magic happen. But you can do this by hand. You're just setting when is 750 over 1 plus 74 e to the negative 0.526x. We should use t, I'm not sure why they switched to x here, equal to 375. So let's multiply the denominator. Then we're going to want to divide by 375. .526 t. subtract 1. Divide by 74. Take a natural log. And finally, divide by negative 0.526. So in this example, the suggestion is just use the calculator. If this were an exam, that would not be acceptable. Okay, we do not accept the calculator gave me the answer as an allowable sort of way to do a problem. You can certainly use this to check your answer, but you need to be able to go through this work and then give an approximation. Okay, the book is going to give us one in just a moment. So if you want to copy down the work we just did, go ahead and do that. I'm about to clear it. So pause if you need to. Okay. So if we just use the calculator to evaluate that to us, it'll be 8.18, which is a little less than 8 1/5 hours, so a little less than 8 hours and 12 minutes. Okay, another example. Okay, a certain way to predict how much wood product you can get is given as below. Okay, so there's 4 classifications: short, medium, medium short, medium long, and long-term products. So based on some data obtained, the percentage of wood products after T years, the percentage of remaining, wood products after T years for long lifespan things is given by the following expression. If you're talking just stuff meant to be used for a long time, here is a model that tells me how much is left after T years. What's the decay rate? So sorry, you should probably copy down this function so that we can use it on the next slide. Okay, hopefully we copied that down. Pause if you need to. We're going on. What's the decay rate? What percentage remains after 15 years? How long does it take to reach 40%? And explain why the numerator in the model is reasonable. That's a pretty open-ended question. We'll see exactly what they mean. So the decay rate is just the absolute value of that exponent multiplier b, which in this case was negative 0.0581, but we take an absolute value, so it's 5.81%. How much is left after 15 years is just evaluate 15, which works out to be about 93.3%. That's good. If it's meant for long-term use, we want a lot of it to be left after 15 years. Okay. When is it down to 40? So we set the end result out to 40 and solve. So multiply the numerator, divide by 40, subtract the 1, divide by 0.031, take a natural log, and divide by 0.0581, and you get 66.6 years. So it takes over 65 years to get down to 40%. And the numerator is the carrying capacity. So the carrying capacity should be some sort of limiting quantity. You want that to be about 100%, and it was just about 100. Okay, so those were a bunch of scientific applications of exponential and logarithmic functions. Uninhibited growth and decay, including radioactive decay and carbon dating, Newton's law of cooling, and logistic models. The fundamental steps of how to solve them were all covered in previous sections: properties of exponents, properties of logarithms. All we did here was use certain given functions that represent different things and solve word problems. Okay, so the next video, we'll do the section all in one video. It's just about taking collections of data and figuring out an exponential or logarithmic function that models it.